All right, so now the t distribution, okay? So it's also called the student's t distribution, and it's a family of related distributions that are all going to depend. Like when I say family, when I say family, like there are an infinite number of different t distributions, and they all depend on a parameter called the degrees of freedom. Okay, and degrees of freedom is tough to understand. I can go over it with you like in class if you want me to, but just to make things easy, we use it to identify which t distribution we're working with. Okay, and it's denoted as degrees of freedom, df. Okay, and it's easy to calculate for a t distribution, super easy. Okay, our degrees of freedom is always going to be equal to n minus 1, so our sample size minus 1. Okay, so t distributions are unimodal, symmetric, and bell-shaped, just like the normal distribution, but t distributions with only a few degrees of freedom have longer tails and a larger standard deviation than the normal. Okay, so let me show you a comparison. Okay, so here at the top, this one right here, wait, let me do a better job tracing. Okay, so this one here, never mind, I'll just look at that where the arrow is pointing. So the top one here, the peak is the highest and the tails are the shortest. That's our standard normal distribution. That was when we used our z statistic. Okay, the next one down is a t distribution with a degrees of freedom of 20. Okay, and the next one down from that, the third one, is a t distribution with a degrees of freedom of 4. Okay, and notice how as our degrees of freedom decrease, the peak decreases, but also the tails on either end of the distribution also get fatter. Okay, and then on vice versa, whenever our degrees of freedom are increasing. Okay, you might notice, well, okay, as our degrees of freedom are increasing, as we hit an infinite number of degrees of freedom, we end up back at the normal distribution. Okay, so that's sort of how it works. Like as our sample size increases, we get closer and closer and closer to our normal distribution. Okay, so that's just a brief example of like what the t distribution is and why we have to use this degrees of freedom idea. Okay, so now we're going to use our calculator here in just a second about calculating our t star. Okay, it's going to be very similar, but we can't use the inverse z anymore, inverse norm. Okay, because inverse norm gives us a z star. We got to worry about finding our t star. Okay, and that's going to be using a different distribution called the inverse t. Okay, so I know we got a lot of like stuff like throwing around, but you just got to sort of memorize all this stuff. Okay, so it works much the same way. So let's say we want to find some our t stars this time. So t star in this interval. So let's say this is our c percent. Okay, it's the same exact idea. Okay, so we're still going to have our tail probability here, still going to probability here, trying to figure out our confidence interval, or our confidence level. Sorry. Okay, so it's still all that calculates the same way, except now in our calculator, it's going to ask us for the area just like it did for inverse norm, but then they also add in that degrees of freedom part. Okay, so I'm going to go ahead and do one of these with you, and then I'm going to have you try a couple on your own. Okay, all right, then you can unpause the video. Okay, so for 90%, okay, that means we want to have 90% here in the middle. Okay, and they give us a degrees of freedom of 5. Okay, so, or sorry, not degrees, they give us a sample size of 5, sorry, which means degrees of freedom is going to be 5 minus 1, which is going to be 4. Okay, and then we worry about our area. Okay, so we got to figure out what's the area in one of these tails. Okay, well, there's 90% in between, so there's 10% outside. That means in this tail, it is 0.05 for our area. Okay, I'm writing all this down for you. Okay, so we throw all that in our calculators. We're going to hit second distributions. It's going to go down to inverse t this time. Okay, and it asks me for the area. I want 5%. And then it asks me for degrees of freedom of 4. We throw that in our calculator, and we're going to get a t. Remember, we're going to use both the positive and negative later on, so just you don't have to write both. So I'm going to go with 2.132. Okay, so now go ahead and try the other 3 here, and then unpause the video and check your work. I'll just make this a little bit quicker. Get this 24. We have an area of 0.05 again, gives us a t star of 1.711. Okay, this one, we have a degrees of freedom of 17, area of 0.025, and a t star this time of 2.11. And then the last one, degrees of freedom is equal to 35, area is 0.0005. That makes our t star 2.724. All right, moving on. Okay. So now we're going to run through this again, okay? But now a little bit of a difference is now we're going to have an unknown population standard deviation, okay? So when the conditions are met, a C% confidence interval for a proportion, or an unknown proportion mu, that should say parameter. I'm like, don't know where I was trying to go with that. Unknown parameter, not proportion, mu, is x bar plus minus t star times our sample standard deviation over the square root of n. Okay, so notice the only things that changed, we got a t star, and we have our population standard deviation. Okay, so those two things changed from our initial formula we talked about in the first video. Okay, so where t star is a critical value for the t distribution with a C% of its area between negative t star and positive t star, this is called a one sample t interval for me. Okay. All right, and just a quick rundown of our conditions. Of course, we have to have random sample or random assignment. Okay. When sampling, we've got to check the 10% condition. We have n is less than 10% of our population, or an experiment, we don't have to check that. Okay. And then normal, this is the one that's a little bit weird, or it's a bit different from proportions. When n is greater than 30, the central limit theorem tells us it'll be the sampling distribution will be approximately normal. When n is less than 30, okay, we have to do one of two things, okay? Have the original population be approximately normal, or we can graph the sample data to make sure there's no outliers or strong skewness, okay? So we're going to check with that later on. Okay, that's a new topic to talk about. Okay, all right. So, look at an example. All right. So it says you recently read an article that said averaging 300 minutes of exercise a week will help fend off cancer, and a random sample of 10 U.S. adults was taken, and they were asked how many minutes of exercise they get each week. The data is below. So it says to construct a 95% confidence interval with the true population mean. Based on this confidence interval, do you believe that adults are exercising enough to ward off cancer? And explain. All right, so let's see. Got to talk about things. Okay, so our mu this time is the average minutes of exercise adults get each week. Okay, let's see, our sample size this time was 10. Our x bar, and we can throw this in your calculator. You don't have to write all of this down where your x bar is concerned. Or you don't have to write down, you do not have to write down the calculations for how you got x bar. You just have to say it. So in this case, we get 283.2. Our standard deviation is going to be 22.04. Our degrees of freedom is 9, n minus 1, so 10 minus 1 is 9. And a 95% confidence, 95% C, sorry, is going to give us a t star, or inverse t for this one, of 2.262. All right. All right, I'm running out of room. Okay, I'm going to have to get a separate sheet. Okay, so I'm going to go ahead and I'm going to check our conditions, and then I will erase this and then come back to it. Okay. All right. So let's see. Are we random? Okay. Yep, random sample is taken. Was taken. Okay. Independent. Okay. 10 is definitely less than 10% of all adults who exercise. And then let's check normal. Okay. All right, we have to worry about, okay, n is less than 30, so that means we can't use the central limit theorem. We aren't given any information about the population being normal. So in this case, we have to take a moment and graph our distribution. Okay, so I will just give this really quick. Let's see, we're going to have 240, 250, 260, 270, 280, 290, 300, 310, 320, 330, and 340. And then a frequency of, let's see, we got 1, 2, 3, 4. Okay, here we're going to have 1. Oops, that's not the wrong spot. So it goes to 260, sorry. And then to 280, we get 4. Oh, sorry, 3. Dang it. 3. And then to 300, we get 4. And then to 320, we get 1. And then 1 for 340 to 340. Okay, and I can see that the data has no outliers or strong skewness, okay, which means sampling distribution will be approximately normal. You can read that, normal. There we go. All right, so I'm gonna go ahead and pause the video here because I've run out of room and I need more paper. But yeah, so I'm gonna erase this and then we'll come back to it for like the last